Welcome back to physics. This lesson is about Newton's first law. So by the end of this lesson, you should be able to say what Newton's law means and then use it to predict and explain things like why a car has got a maximum speed even if you absolutely floor the accelerator, and why a skydiver, when they jump out of an aeroplane, eventually reach a constant speed. Before we get into that, we're going to do a bit of recall practice on some basic things to do with forces and force diagrams, because you might have forgotten that from last time you did it. It might have been a while ago. Okay, so pause the video and have a go at the quiz. All right, some possible answers. A scalar is a quantity that only has size or only has magnitude. It doesn't have a direction. Remember, magnitude is just a fancy word for size. A vector has got a magnitude and a direction. Friction is a force that opposes motion caused by materials rubbing together. So friction is a contact force. Air resistance is a kind of friction caused by air particles rubbing over something that's trying to get through it. So air resistance is friction caused by the air. Upthrust is a contact force produced by a surface and it's pointing upwards. So if you're sitting on a chair at the moment, there's an upthrust force from the chair on you, holding you up. Thrust force is a forward force. For example, a car would get a thrust force from its engine. Weight and gravity, I'm going to take them together. They're not quite the same thing, though lots of people think they are. Weight is a force caused by gravity acting on your mass. So you have a certain amount of mass, and as long as you are in, for example, the gravitational field of the Earth, you'll feel some weight. But if you were out in interstellar space, where the gravitational fields are very small, you wouldn't have any weight, but you still have mass. Number 9, terminal just means end. You'll have heard terminal possibly in electricity before. We talk about the terminals of the power supply or the terminals of a battery. We just mean the ends of it. In this context, we'll be using terminal velocity to mean the end velocity. And number 10, resultant force is what you get when you have several forces acting on an object. You add up all the forces in one direction, and then you take away all the forces that are in the opposite direction. So you're adding forces, but taking account of their direction. Okay, now for the first section of the PowerPoint, if you find that it's a bit simple, you think, well, actually, I know all about forces and force diagrams, then feel free to skip through it. You can always come back if you find you need to. If you want a gentle introduction to Newton's first law, then just keep going at my speed. All right, so a force diagram is exactly what you think it is a diagram of forces. So here's a football, and when it's there, imagine it's in the air, it'll have two forces acting on it. It's got some weight pulling it down, and it's got some air resistance trying to oppose the weight. And we can see from this diagram the weight is bigger than the air resistance. So that football is accelerating downwards. So key points, we use the force diagram to tell us the relative size, the direction, and the name of the force. However, you don't necessarily want to draw the object every time. I mean, drawing a football is relatively easy, but what if you were trying to draw the force diagram for a car? That's a lot harder to draw. So in physics, we make it easy. We're a little bit lazy, to be honest, physicists. We don't bother drawing the object. We represent it with a single point at the object's centre of mass. So there's the football, a single point, and we just draw the force arrows on the point like that. Here are some more examples. For each one, we've got a car, a boat, a fish. We don't need to draw a car, a boat and a fish. We need to draw a dot for each one. And then we add the forces onto our dot. So for the car, we've got the weight acting downwards, and then we've got upthrust from the road acting upwards. The car isn't accelerating up or sinking through the road, so those must be equal and opposite. We've got thrust force from the engine forwards, and it's braking, so the friction force backwards must be bigger than the thrust. A sailing boat staying still. We've got weight acting downwards and upthrust acting upwards. Those are equal and opposite. That's a pair of balanced forces. We've got thrust acting forwards and friction acting backwards, and those are balanced as well. So that sailing boat isn't accelerating anywhere. Fish accelerating upwards. We've got the weight acting downwards, and the upthrust from the water must be greater than the weight to make it accelerate upwards. So we've got a resultant force acting upwards. Right, I want you to pause and draw a free body diagram for each of these. Remember, we've got a lorry, a kestrel and a submarine. You do not have to draw a lorry, a kestrel and a submarine. Just do a dot for each one and then add the forces to the dot. Okay, pause the video. Answers. There's the lorry. It's going at a constant speed. The forces will be equal and opposite. Force causes a change in motion. So if the resultant force is 0, the motion doesn't change. I'll get into that in more detail in a few minutes. Kestrel hovering, upthrust and weight are equal and opposite. Submarine accelerating down, the weight must be bigger than the upthrust. Right, the motion depends on the resultant force. If the resultant force is 0, there's no change in the motion. And to get the resultant force, you add the forces together. Add all the forces in one direction together, and then take away all the forces in the opposite direction. So for this crate, we've got 30 newtons to the right and 50 newtons to the left. So I've got to take away. So my answer will be 20 newtons to the left. So when you're giving an answer about a resultant force, you can't just give the 20 newtons, you have to give the to the left bit as well. It's a vector, you must give the size and the direction. So here's a few more examples. By all means, pause the video and go through it. If you need some more help, I'm going to talk through it anyway. First one, we've got 7 newtons to the right, 4 newtons to the left. 7 take away 4 is 3, so it's 3 newtons. The biggest force was towards the right, so it's 3 newtons to the right. Number 2, we've got 2 forces acting towards the right, so we've got to add those together, the 105 plus the 80, and then take away the force to the left. And we end up with 15 newtons to the left. Number 3 is a nice easy one. Number 4, we've got 1,200 newtons pointing to the right, and then we've got 750 plus 550 pointing to the left. So the two that are in the same direction, we add them together and take away the opposite one, and we end with 100 newtons to the left. Number 5, we've got 115 newtons to the left and 115 newtons to the right. Those we take away and end up with 0. And then we've got 70 newtons up and 50 newtons down, so we end up with 20 newtons up. When you are doing your resultant force, look for pairs of forces that are opposite each other. So in that last example, I have to treat the 70 and the 50 separately from the two lots of 115 because they're not in line with each other. All right, pause the video. This should only take you a few minutes and work out the resultant force for each of these. Remember, you give the size and the direction. Are we ready for some answers? Okay. Moving on to Newton's first law of motion. Now we're solid on resultant force. I've said it a couple of times already. If the resultant force is zero, it won't change the way an object is moving. So whatever the object was doing, it'll keep doing that. So there's two situations. If you've got an object that wasn't moving, then it'll remain stationary. So if an object was stationary, it remains stationary. If the object was moving, it continues to move at the same speed and in the same direction. So that second point there is one that sometimes people forget about Newton's first law. There's this tendency to think that if something's moving, there must be a force moving it. That's not necessarily the case. If the movement is changing, there must be a force causing that change. But if we've got some kind of constant motion, so a constant velocity, then there is no resultant force. Okay, let's have a look at these. So we've got an exam question here. We've got horizontal forces acting on a car, 800 newtons one way, 800 newtons the other way. So the resultant force is 0. And we have to choose the correct statement from the list. So it looks like there might be two answers, because it can't be slowing down or speeding up because there's no resultant force to cause any change. So it's either got to be stationary or it's got to have a constant speed. So we've got to pick which is the best answer out of those two. And it doesn't tell us whether the car was already moving or whether the car was parked. However, if there's a thrust force from the engine and there's an air resistance force acting backwards, that suggests to me that that car is actually moving. So it will have a constant speed. Another way you could look at it is to say, well, it will have a constant speed, and a special case of that would be if the speed was 0, and then it would be stationary. The next one, we've got a person using a jetpack. So we've got the person's weight, we've got the upward force upwards, and the condition necessary for the person to be able to remain stationary in midair using Newton's first law. If they're stationary, there's no resultant force, so the upward force must be equal and opposite to the weight. Right, pause the video and have a go at this question. Ready for an answer? Resultant force is the sum of all the forces taking account of their directions. Or you could have said it's what you get when you add up all the forwards forces and then take away all the backwards forces, and you've explained the same thing. Part 2, describe the movement of the aircraft when the resultant force is 0. Well, the movement won't change, so we've got to look up at the top of the question and find out what was the movement as it moves along a runway. Okay, so it is moving, it's not stationary. Constant speed in a straight line. Or you could have said constant velocity. And that question was actually worth 2 marks. 1 mark for constant speed, 1 mark for in a straight line. Or 2 marks if you went for constant velocity, because velocity implies direction. Okay, pause the video and answer these ones now. Ready for some answers? Okay, let's see if we can now apply what we know. Terminal velocity, remember I said that meant the final velocity, the last velocity. Well, every car, no matter how powerful the engine, even if you absolutely floor the accelerator, it will have a top speed. It will accelerate only to a certain point, and then it won't accelerate any further. So here are 3 identical cars. One's going at 1 metre per second, one's going at 10 metres per second, one's going at 100 metres per second. Now, any car has got a maximum thrust force that it can produce, and that depends on the power of your engine. So let's put the thrust force identical on each car. Those are the same. However, the air resistance is not constant. You've probably felt the effect of air resistance and speed. For example, if you are cycling and you're going really fast and you feel the wind in your face, or if you're running and you feel the wind in your face, air resistance gets bigger as speed gets bigger. So let's add air resistance in here. There we go. And that kind of makes sense, because if you're trying to go through the air at 100 meters per second, then the air molecules are going to be hitting you pretty hard compared to how they would be at 10 meters per second or 1 meter per second. So eventually, the air resistance gets bigger and bigger and bigger until it's equal and opposite to the thrust force from the engine. And if the forces are equal and opposite, that means the resultant force is zero, and there's no more change to the way that car can move. So that car is going to continue at a constant velocity. That's a constant speed in a straight line. So let's look at a velocity time graph for that car. So imagine that you've got into that car and you've started from rest, you've floored the accelerator, you just want to see how fast it's going to go. Safety note, don't ever do that. For in the first part, the car will accelerate. And during that time, the thrust force is constant, but the air resistance is increasing as your speed increases. Eventually, we reach a constant velocity because the resultant force equals zero. And that constant velocity is called the terminal velocity. Okay, that's for a car. We're going to look at another case of terminal velocity, and that's for a skydiver. So here's our skydiver. Now if you look at the arrows, we've got the weight arrows all pointing downwards are all the same length because the skydiver's weight is not going to change. It's the air resistance that changes. So in the first diagram there, the air resistance is very small. The skydiver has just jumped out of the aircraft, so they're not going very quickly, so the air resistance is small. But as they accelerate, because the weight is bigger than the air resistance, there's a resultant force downwards that makes them speed up. As they speed up, the air resistance force increases until eventually the air resistance and the weight are equal. So the skydiver, before they open the parachute, they'll be falling at a constant speed. As soon as they open the parachute, the air resistance force gets very large very quickly. So there's now a resultant force upwards, which pulls on the skydiver and makes them slow down. They're still falling downwards, but they're decelerating. So how do we put all that into words? When you're explaining Newton's first law on terminal velocity, it's a good idea to write kind of bullet points or clear linked steps. So I'm going to scroll through the answers and you can read them without me talking over it. Let's have a look at what the skydiver's velocity time graph would be. At first, We've got acceleration because weight is bigger than air resistance. So we've got a resultant force downwards and the skydiver accelerates down. Eventually, the air resistance becomes equal and opposite to the weight. So the resultant force is 0. And we have a terminal velocity. We've got a constant velocity. The parachutist opens the parachute. The air resistance is now huge because the surface area is much larger. Therefore, they decelerate. So the velocity reduces. As the velocity gets smaller, the force of air resistance gets smaller again until the air resistance and the weight are equal again and they reach a new lower terminal velocity which lets them land safely. Okay, I want you to pause the video and do the exam questions worksheet. Take about 20 minutes on it. The first question is foundation, so if you think that's too easy for you, then skip the first question and start with question 2. And question 5 is higher tier. The ones in the middle are all standard demand questions. Okay, here are the model answers to the Newton's first law exam questions. Now you'll notice the title was Newton's first law, mostly exam questions. It's quite rare to find exam questions that are just specifically on one single thing and nothing else. So be prepared for a bit of mixing and matching of equations. Right, question 1a, we've got two forces acting on an object. I'll be to tick the box for the resultant force. Well, I've got 6 newtons to the right, 2 newtons to the left, so I've got to take away 4 newtons and it's in the direction of the bigger force. It must be 4 newtons to the right. Nice gentle start. Part B, we've got a question about base jumpers and a picture of a guy in a wingsuit. So this base jumper accelerates forwards when force A, mine's clipped off the page there, force A is forwards, is, if he's accelerating forward, it must be bigger than. The base jumper falls with constant speed when force C, well there's C and D must be equal. If the forces are equal and opposite, then the resultant force is 0 and you'll get a constant speed, no change to the motion. Part 2. To land safely, the base jumper opens a parachute. What effect does opening the parachute have on the speed of the following base jumper? Slows him down. Or you could say reduces the speed. Or you could have said decelerates. Give a reason for your answer. Greater surface area. Therefore, greater air resistance. Okay. Let's do 2 and 3 next. Question 2. We've got an electric powered go-kart and we can see a picture of it there, we can see the shape of it. Suggest 2 changes that could be made to the design of the go-kart to increase its top speed. You could go for something to do with streamlining. So make a more streamlined shape. And you could give a suggestion of how to do that. For example, make the front of it narrower, make the driving position much lower. See, he's sticking out a lot there. If he was sitting a bit lower down, he wouldn't have as much air resistance. For the second one, you could make another change. You could make it lighter, so less mass. So make it out of lighter materials, and then for the same forwards force it's going to accelerate more quickly. And you'll get more about that in our next physics lesson when we do Newton's second law. Now we've got a graph question. So we've got the velocity time graph for the first 40 seconds. Between which 2 points did the go-kart have the greatest acceleration, and give a reason. So it's going to be A to B. Give a reason, steepest gradient. So 1 mark for picking the correct answer there, and 1 mark for saying steepest gradient. You had to have picked this answer. You know, if you got that one wrong and then got this one right, you would lose that mark as well. So you must have ticked that box. Question 3. We've got 3 cars being driven along a road. We've got the forces on each car, and we have to describe the motion. It's only 3 marks, so we're looking for something fairly simple. If there were more than 3 marks, they'd be looking for an explanation as well. So they're being driven, so they're moving. So A would be constant speed in a straight line. Or you might have said constant velocity, because velocity means speed with direction. B, the thrust force is bigger than the air resistance forces, so that one must be accelerating. So you could have said either accelerating or speeding up, getting faster. And this one, the backwards forces are greater than the forward forces, so that one is decelerating. Or you might have said slowing down. Right, question 4. We have a skydiver. So after 10 seconds, the skydiver is falling at a steady speed. So we've got a time, we've got a speed, then opens her parachute. After another 5 seconds, she's once again falling at a steady speed. The speed is now only 10 meters per second. Calculate a skydiver's average acceleration during the time from when she opens her parachute until she reaches her slower steady speed. So we've got to sort out from this data, what do we actually need? So we're asked from when she opens her parachute. So when she opens her parachute, that's our start, and she opens her parachute when the speed is 50 meters per second. Remember this equation from 2 videos ago? After 5 seconds, so we've got the time, so the initial 10 seconds there at the top, that's a bit of red herring information that we're not going to use. New speed is 10 meters per second. So we've got our data, we have to calculate the acceleration. A equals v minus u over t. If I substitute in, there we go. So I think in your version that actually said 4, and it said give the unit up here. So the marks there are for knowing the equation, substituting the correct numbers into the equation, getting the answer, and getting the units. Part B. Explain as fully as you can why the skydiver eventually reaches a steady speed with or without the parachute. So we're looking for points in your answer to say constant weight down, air resistance upwards, increases with speed. So if you've got the idea that the air resistance gets bigger as the speed gets bigger, and then eventually air resistance equals weight, or a better way to say it, equal and opposite to weight. So the resultant force is 0. And there's no further change to the motion. So there we've applied Newton's first law. Second part, explain as fully as you can why the skydiver's steady speed is lower when her parachute is open. So we're looking for the idea that at any speed there is a greater force of air resistance. Or at all speeds. Okay, now this is not a foundation question. This is a standard demand question. So on the foundation paper, foundation question earlier, you just had to say the air resistance had increased. But for this one, you've got to have a little bit more detail to get the mark because it's a higher level of question. Okay, last question. Got a racing driver along a straight and level road. The driver pushes the accelerator pedal as far down as possible. The car does not accelerate above a certain maximum speed. Explain the reason for this in terms of the forces acting on the car. So it'd be a good idea to label what the forces are. So I'm going to annotate the diagram. So I'm going to say thrust and air resistance. Because one of the marks of those 4 marks is for identifying what the forces are. So what could we say? There's a maximum thrust from the engine. And air resistance I might label that one forwards. I've already done it on the arrow, so I probably don't need to write that since I've got it on my diagram. So air resistance backwards increases with speed, or as the speed increases the air resistance increases, something like that. And eventually these forces are equal and opposite, so the resultant force is 0. So there can't be any acceleration.